The purpose of this talk is to give a very high-level overview of audio machine learning in the form of neural networks, specifically model architectures. Those are the main building blocks in the sense that they are the actual wirings doing all of the computation. I hope that this can serve as a starting point for exploring different approaches and methods, especially if you're new to machine learning or if you have an idea for a specific project and want an overview of what generally works in different contexts. Now, of course, from a helicopter perspective, it's not always possible to see all the details, but hopefully we will see the big picture. Let's begin by examining what machine learning models are designed to do, the tasks or applications or problems that they are built to solve. These include various forms of transformations, generation, classification, segmentation, transcription, just to name a few. And as we can see here, the task can be framed as mappings across modalities. A modality is the kind of data a system operates on and is defined by its source or information channel. Examples are audio, images, and video, but it can also be more symbolic representations like text. In audio, we have symbolic representations like musical scores, MIDI notes, or even control parameters such as for synthesis. A representation is the concrete form of a modality as it's presented for the model. In audio, we have raw waveforms, spectrograms, or discrete tokens. In short, modalities will always be given by the task, but representations can be chosen according to other requirements. And not all representations are suitable for a given architecture or training setup. The premise of machine learning is to take data and feed it into a computational model, in this case a neural network, which transforms it into new data in the form of predictions, classifications, signals, or other output. The model is trained by adjusting internal parameters via a clever class of algorithms known as backpropagation. This is to minimize a loss function across many training examples. The system learns patterns and structures, allowing it to generalize beyond the explicit examples. So what is a neural network? Well, if we zoom in to the lowest level, a neural network consists of nodes or cells called neurons in a directed graph. Each neuron forms a linear combination of all its inputs, and then it applies an activation function, and then it outputs the results to the next neurons. An activation function is a nonlinear mapping, and it's crucial to model complex behaviors. Some activation functions pass only positive values, and others squash the input into a fixed range. Now, if we zoom out again a little bit, we can see that those neurons are usually arranged in layers. We have an input layer at one end and an output layer at the other. And as data moves through these layers, they can represent more and more abstract or higher level features. This kind of fully connected networks, or multi-layer perceptrons, as they are sometimes called, are essential building blocks in almost all model architectures. But they are seldom used all by themselves. While they can identify and interpret patterns, this performance comes at a large computational cost, and it doesn't always scale well to the kinds of tasks that we care about. There are much more efficient ways where we can exploit the fact that audio contains local patterns that repeat at different scales. Patterns or features can be captured much more efficiently without connecting every neuron in one layer to every neuron in the next. And this is what happens in a convolutional neural network, where we make use of convolutions. These are similar to digital finite impulse response filters. They have a relatively short set of coefficients that are applied repeatedly, sliding across the input or each layer. As with any of the architectures, the input is not always a single channel. It can be multi-channel, stereo, microphone arrays, multiple stems in music. As long as the channels are meaningfully correlated in one way or another, it can provide extra insight and improve performance on tasks. No matter the input channels, in a convolutional network, each layer usually applies multiple filters. And this means that the representation grows in one more dimension than the input signal. These extra channels that are emerging are called feature channels. And that is because each filter becomes a detector for a feature. As we progress through the network, the sequence length usually becomes shorter by the use of pooling, stride, or other downsampling. So feature channels increase, but other dimensions shrink. Depending on the whole setup and what we want to achieve, if we compress the dimensions a lot, we get a bottleneck. And this can compress the information because the network has learned common patterns in the training data. Bottlenecks can be useful for many purposes: dimensionality reduction, forcing feature abstraction, and reducing computation. For example, we can produce embeddings, compressed representations that are also used for many purposes. Or we can make what is known as an autoencoder. It has an encoder part which compresses the signal into a very compact and lower dimensional representation in the so-called latent space. Then a decoder reconstructs the signal back. Variational autoencoders extend this by adding some amount of randomness. This enables generative use and variation, like interpolation between sounds. A U-Net is an architecture which is kind of shaped like a U, and this basically an autoencoder, but with skip connections between corresponding encoder-decoder layers. Skip paths let the decoder reuse fine-grained detail, which could otherwise be lost in the compressed bottleneck. And this makes it far better than a plain autoencoder for tasks needing both global context and local precision, like denoising or source separation. Jumping back to CNNs a little bit, they can have a range of dimensions. For audio, we usually use 1D or 2D depending on the representation. So for PCM waveforms, they're usually 1D, and 2D for spectrograms or other time frequency representations. But CNNs come with issues. Filters are short, so much downsampling is needed before neurons can hear what is going on in larger timescales. This scale is known as the receptive field. downsampling also means that fine detail can be lost. And for streaming, the input must be chunked, which further limits context. Recurrent neural networks fix some of these problems. They process sequences step by step and carry hidden state forward for each time step. These are updated with new input, and it gives the model an implicit memory. The hidden state can then influence later output. RNNs can in principle handle infinitely long sequences. The most efficient RNNs in use today are long short-term memory and gated recurrent unit. They mitigate some of the training issues that plain RNNs can have by clever gating mechanisms that control the flow of information. They regulate what information is either stored or discarded or exposed at each step. They can be bidirectional, so they can look forward as well as back in time, depending on the training setup. Even with these gating mechanisms, though, at each time step, very long-term relationships can get lost. And also, because of their sequential nature, the training is more difficult to parallelize, which in practice means slower training. Another way of handling these problems were addressed by transformers introduced in 2017 for translation between languages. It was later used for text generation, image processing, and audio. The main innovation is the concept of attention. And this is a way for the model to decide what parts of the sequence should influence each other. In effect, it creates a map of relationships across the entire sequence. And this allows points far apart to exchange meaning. Multiple heads do this in parallel. Each head learns to focus on different aspects of relationships. So this can be local continuity or long-range structure, or some other subtle correlations. And then this whole attention thing repeats through stacked layers, just as in the other architectures. There are two flavors of attention. For single sequences, self-attention is used, and this is what's used in most language models. When we cross modality boundaries, we often use cross-attention, where the attention calculation is performed between two different sequences, often in an encoder-decoder setup. The input representation for transformers is often MEL spectrograms. Other representations are tokens produced by some vector quantization process or a neural codec like encodec. To see an example of transformers in audio, we can look at the whisper transcription system, which was introduced a few years ago. It uses this kind of encoder-decoder configuration. The encoder processes audio into complex features, and the decoder generates text tokens step by step. The cross-attention connects the text token generation back to the encoded audio features. And the decoder also uses self-attention at the same time. The multi-head attention can capture both short and long-range relationships like phonetics, prosody, rhythm, semantics, or other kinds of overall structure, all in parallel. One problem with transformers, though, is that the computation scales quadratically with input length, or the context it can operate on. A somewhat different approach, introduced surprisingly recently, is differential digital signal processing. This builds neural nets around classic DSP blocks like oscillators and filters and reverbs, which are implemented as differentiable modules. So instead of generating audio sample by sample, the model predicts control parameters for these blocks, while the DSP handles the actual waveform. Traditional audio ML has to brute force its way through spectrograms or raw samples, wasting capacity, only then to rediscover already known structures. DDSP shortcuts this. It leverages existing audio knowledge. This is more efficient and interpretable and produces high-quality sound with less training data and less compute. This has been used for many different tasks in music, speech, and sound synthesis. Because, as we have seen, all of these model architectures have different shortcomings, hybrid architectures are common. For example, combining CNNs, which are good for local feature extraction, with RNNs or transformers that are better at capturing long-range dependencies. A generative adversarial network trains two networks at once, connected together. A generator that produces candidates and a discriminator that judges them against real data. And this adversarial setup forces the generator to improve until its outputs are indistinguishable or very close to real examples. GANs have been used very successfully for speech synthesis, music generation, and upsampling tasks. Diffusion is a method combining a specific training setup with an architecture, often a U-Net, since, as mentioned, it's good at denoising. The model is trained by adding noise to a clean signal and learning to reverse that process step by step, so that even pure noise can be turned into a plausible signal. And this interesting figure shows the noise distribution on the left, and it also shows the distribution of the real training data on the right side. And it shows the sequence of steps in between, gradually turning noise into something that resembles real data. In a generative task, it can produce very diverse and high-fidelity samples. And in denoising, it's also very powerful. But it is computationally expensive, both in training and in inference. So it's far from real-time ready. Summing up, we can see that practical trade-offs will always exist between fidelity, latency, accuracy, compute, long-term context, and training data requirements. And in all cases, it always depends on the task. Now, let's see what we can achieve by using some of these architectures and techniques.
It turns talking into text. And you don't have to speak slowly. In fact, you can talk as fast as you want.
This is the Micro Machine Man presenting the most midget miniature motorcade of Micro Machine. Each one has dramatic detail, terrific trim, precision paint jobs, plus incredible micro machine pocket playsets. There's a police station, fire station, restaurant, service station, and more.
The rabbit hole went straight on like a tunnel for some way, and then dipped suddenly down. The rabbit hole went straight on like a tunnel for some way, and then dipped suddenly down.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
If the supply of fruit is greater than the family needs, it may be made a source of income by sending the fresh fruit to the market.
Baby shark, do diggly do. Baby shark, do diggly do. Baby shark, I mean snow.
Yellow way, that's a push.
I wish you all happy experimentation and development.